Good afternoon, everyone. Welcome to the IOA and welcome to the 2024 Eddington lecture. I should thank a few people for supporting this. So this lecture has been going on for many years, and that's only possible because various people and organisations continue to give their support. So the Royal Astronomical Society should deserve a mention because they very generously support this. In fact, Steve will be going down to London tomorrow to talk again to the Royal Astronomical Society in London as well. And also we should mention the support of Professor Donald Lyndon Bell, who many people here will know and was director of this institute more than once in the past. And a number of years ago made a very generous donation which continues to support this series of lectures as well. So this year we're delighted to welcome Steve Taylor back to the IOA to give the Eddington lecture. So Steve, originally did an undergraduate degree in Oxford in physics, and then came here to do his PhD, which is where I met him. We overlapped as PhD students. So as a PhD student here at the IOA, this was in the era before the first detection of gravitational waves. Both Steve and I worked on gravitational waves. Steve originally, he worked on a range of topics in gravitational waves during his PhD, initially with with LIGO data, or simulated LIGO data as it was then, and cosmology and looking at measuring the Hubble constant. But during the second half of his PhD, he started to get interested in pulsar timing, which is where the field where he's become an expert and which is what he's going to be talking about today. After graduating, Steve went to Caltech for postdocs at both JPL and Caltech, or JPL and Caltech, where he joined the NANO Grav collaboration, so the North American nanohertz-frequency observatory, or words closely to that effect?
Close to that, yeah.
Close enough to that. I'm sure at some point in Steve's talk he'll give you the correct acronym. So Steve has risen to be a leading member of that collaboration. He led the analysis of the data in 2023, which made the first, or presented the first evidence for an ultra-low frequency stochastic background of gravitational waves. So 2023, the year we've just had, was kind of the annus mirabilis for pulsar timing, when multiple collaborations, large collaborations on 4 continents actually, all announced the first evidence for this. So it was really a breakthrough year for pulsar timing. Steve is currently the chair and the spokesperson of the NANO Grav collaboration, and he's received several prizes during his career to date. Most recently, he was named the Kavli Plenary Lecturer by the American Astronomical Society as well, which is a great honour. So we're very happy to be able to welcome Steve back to the IOA to give the 2024 Eddington Lecture on the dawn of galaxy-scale gravitational wave astronomy. Over to you.
Thank you very much, Chris. Afternoon, everyone. It's really an honor and a personal highlight to come back here and talk to you about results, real results of things that I was simulating and working out while I was a PhD student here. And even if I'd forgotten this morning what I was supposed to do this afternoon, my bus in reminded me that I was supposed to go to Eddington and to give a talk today. As Chris mentioned, my brief history of my sort of world line, hopefully partial world line, is that I started off in Northern Ireland before going to the other place, unfortunately, for my undergrad, before coming here for some very enjoyable years as a PhD student, working on these problems, moving on to JPL initially and then Caltech for postdocs, before moving to Nashville, Tennessee in 2019 for my current faculty position. So while I was here at the IOA, I worked with Jonathan Guerre, who was really one of the pioneers of gravitational wave astronomy. And there's the title, Exploring the Cosmos with Gravitational Waves, sufficiently vague because it covered a broad range of things in gravitational waves. But I did want to highlight the date that I handed in the thesis, March 2014. So it's almost exactly 10 years since I handed in my thesis here at the IOA until giving this talk. The broad range of topics, as Chris mentioned, we're measuring the Hubble constant and trying to do other measurements of cosmology using ground-based gravitational wave detectors before taking a segue halfway through my PhD. Originally, the thought was I was going to work on LISA, but at that time, there was a bit of a funding crisis, and LISA was de-scoped, and Jonathan said, well, why not take a look at this mock data challenge for the International Pulsar Timing Array, spend a few months on that, see if anything comes out of it, and I spent the last 10 years, something eventually came out of it, and I'm happy to talk today about the results. So I'll mention several of these topics today, but since we are talking about gravitational waves, even though this is a very expert audience, for any students in the room who are unsure of gravitational wave theory, just a brief refresher of some of the important aspects. So obviously, the modern theory of gravity is enshrined within Einstein's theory of general relativity, where gravity arises from the deformation of space-time geometry. And since you can deform space-time geometry and describe paths in space-time through that formalism, you can also generate wave solutions. Those wave solutions propagate at the speed of light, and within general relativity, you're allowed two polarizations of those gravitational waves, illustrated by these deforming patterns above. So you've got, if you had a gravitational wave that was coming out of the screen or going into the screen, and you had a ring of test masses just arranged in a circle, then the gravitational wave would deform that ring of test masses in either this plus polarization, so over one full wavelength, it goes plus in shape, and then cross. So it's offset by 45 degrees in the other polarization. So similar in some, qualitative descriptions to other kinds of waves. Now, the classic example of a system that generates gravitational waves, the most, largest target population in the universe, are systems of compact binary systems like black holes, neutron stars, or white dwarfs, where as they orbit each other, they source gravitational waves. That emission of gravitational wave causes the orbit to harden and tighten. The gravitational waves get stronger, increase in frequency until eventually the black holes or other compact objects merge together. And we usually describe the amplitude of gravitational waves really in terms of fractional length changes imparted to lengths in space-time. So you have an amplitude that's denoted as a strain, so a fractional change in length. And for a binary system, that's roughly proportional to properties of the binary like mass to the 5/3, frequency to the 2/3, and then very nicely inversely proportional to the luminosity distance to the system. So if you have a system that is going to register in something like the LIGO detector, something that's of order 100 solar masses or smaller, frequencies of order 100 hertz, and then distances of a few hundred megaparsecs, then the fractional length change imparted to an experiment would be 10 to the power minus 21. So that's incredibly tiny. And over the length of something like the LIGO detector, that's a length change, an absolute length change, that's much smaller than the size of a proton. Now, the fractional length changes, the strain, is larger if you're looking for supermassive black hole binaries, which would have masses of order 10 to the 9 solar masses, frequencies 10 to the minus 9 hertz, and then similar distances. So that strain would be of order 10 to the minus 17, which seems several orders of magnitude larger, but still incredibly small, and almost impossibly difficult to detect, especially given the fact that we, as I will describe later on, don't have full control over every aspect of our overall instrument. So these are the kinds of gravitational wave detectors with which you might be most familiar. These are ground-based detectors like LIGO, the Laser Interferometer Gravitational Wave Observatory. There's one in Hanford in Washington. There's one in Livingston, Louisiana. And this is an L-shaped laser interferometer. So this is 4 kilometers on a side here. And laser beams initially start out in phase at the vertex here, are fired along different lengths of the L. And if a gravitational wave impinges and passes through the detector, then it will alternately stretch and squeeze the length of those arms, causing the laser beams to come back slightly out of phase and produce a time-dependent interference pattern that encodes all of the information you need to infer what the source of gravitational waves was and the property of the gravitational wave emitting system. This has now become a huge enterprise and a very, very popular area of astronomy in and of itself. These are the gravitational wave detectors that are the ground-based gravitational wave detectors that are either already operational or currently being commissioned. So you've got the LIGO detectors in the US. There'll also be a counterpart LIGO detector in India. There's GEO 600, which is in Germany. It's more of a technology test bed. Virgo, which is a very important part of the global network, and CAGRA, which is already online but still being ramped up to make an impact on the global network. So this is a big area of astronomy at the moment. Gravitational wave astronomy combined with trying to find multi-messenger counterparts as well. So the field of direct gravitational wave detection has gone from this in 2015, this beautiful, very, very clear signature of two merging black holes, roughly 30 solar masses each. This was on September 14th, 2015. To this, in 2017, the collision and detonation of two neutron stars producing not only gravitational waves, but really a myriad of different electromagnetic signatures that show up in many different bands. That was on 17th of August, 2017, I believe. Yeah, GW 170817. And then this is what the field looks like today. So really tons and tons of binary black hole coalescences and candidate neutron star black hole systems. I believe there are of order 90 in the previous catalog, and then in the first stage of LIGO's observation 4 run, it's almost doubled its haul of binary black holes. So just extraordinary. It's now at the rate of almost one per week that a binary black hole system is being detected. So that's wonderful, but now that this is a successful enterprise, why look elsewhere? Well, we know why we look elsewhere in other areas of astronomy. It's because this is what astronomy looked like in the early 17th century. And if we had only stayed in that small sliver of the electromagnetic spectrum, then we wouldn't be seeing the huge amount of other astrophysics, the other astronomical and cosmological phenomena that becomes available to us if we expand our view and become sensitive to other parts of the electromagnetic spectrum with other detectors. And the same is very much true of gravitational waves. So this is the corresponding spectrum of gravitational waves with prospective sources on top and then detectors along the bottom. So the gravitational waves with which you might be most familiar and that have been detected by ground-based gravitational wave detectors are up here at the high frequency end. And those are mostly in spirals and coalescences of stellar mass black holes and neutron stars, but nothing heavier than about 100 solar masses. What I'm going to tell you more about today are gravitational wave detection methods and the first evidence for gravitational waves many, many orders of magnitude lower in frequencies, down at the nanohertz scale, where we're really looking for not just one source, but an entire population of supermassive black hole binaries all adding together to form a stochastic gravitational wave background. So I'll explain what this curve is more as time goes on, but really this is our smoking gun signature for gravitational waves in our detector. It's the signature of an isotropic background of gravitational waves, passing through and causing timing correlations across many pulsars throughout the Milky Way. Now, we had first announcement in June 2023. In NANO Grav in particular, we had a focus issue in the Astrophysical journal Letters. We had a suite of papers released. There are many more papers and analysis techniques that are being published. And this corresponds to about 4 sigma significance of the low frequency gravitational wave background. And by my rough calculations last night, we're accumulated something like 14 citations per week for this primary evidence paper. And as I mentioned, what we're seeing here is really just a visualization of timing correlations between pulsars that are separated by a certain angle on the sky, which means that when the pulsars are very, very close together on the sky, the timing perturbations caused by gravitational waves are correlated in a positive sense. It then goes down to 0, becomes negative, and then goes positive again. And these data points here are a visualization of our data. We don't condition our detection statistics on it, and I'll explain more of those later. This is sort of the prettiest picture we could form of actually what the correlations look like in our data set. And associated with, we had a nice announcement ceremony at the National Science Foundation in DC, where we were joined by Kip Thorne, the 2017 Nobel laureate in physics, and Jocelyn Bell, who joined us on Zoom, which was a very nice moment to have the person who first saw pulsars right here in Cambridge to actually join us for this great use of pulsars as a detector of gravitational waves. So, as Chris mentioned also, I'll give the full description of what NANO Grav stands for. It's the North American Nanohertz Observatory for Gravitational Waves. And our ground-based part of our detector is comprised of the Green Bank Telescope in West Virginia. It was using the Arecibo telescope. Unfortunately, that's no more. It collapsed in 2020. But I'm sure everyone here is familiar in principle or has seen it in pictures or movies It's a very, very famous telescope. We also use CHIME, the Canadian Hydrogen Intensity Mapping Experiment, for low radio frequency timing, and then supplementing observations using the VLA in New Mexico. We're a large collaboration, at least large, we think we're large. We're not large by LIGO standards, but we have about 190 members spread across something like 70 institutions. And not all of those institutions are actually in North America anymore. We have some people in Germany and other parts of Europe that are working with us. It initially started out as a collection of radio astronomers and then grew to include gravitational wave scientists and then compact object astrophysicists. And now within the last year or two, high energy physicists and people working on early universe cosmology theories as a way to test their theories against what we're finding. So all are welcome to join and contribute. If you have a particular theory or a model that you'd like to apply to the data are public, but if you'd like to join and actually contribute to the primary analysis efforts, talk with me or see the website. It's all very easy to get involved if you'd like to. And I'm somewhat biased because I'm chairing NANO Grav, but really this is a global community of people that are dedicated to searching for gravitational waves at the lowest frequencies we can access at nanohertz frequencies. And that includes the European pulsar-timing array, which is the collaboration that I started out in when I was a PhD student here, and has access to lots of great radio facilities. It also includes the Parkes pulsar-timing array using the Parkes radio telescope. And then we have new collaborations that are joining the international community, including the Indian pulsar-timing array using the giant meter wave radio telescope, and then MeerKAT, which is the Meer-Time pulsar-timing array, but it's using MeerKAT, which is the precursor instrument to the square kilometer array. And then a fantastic instrument, which is FAST, the 500-meter aperture spherical telescope in China, bigger than Arecibo ever was and just got phenomenally sensitive observations. And in June of last year, all of these major collaborations reported varying degrees of evidence for the low-frequency gravitational wave background. Within the international pulsar-timing array community, NANO Grav had the strongest evidence, but the different degrees of evidence reflect the varying sensitivities of those data sets. Now, these radio telescopes are really just the Earth-based portion of our instrument. The other part of our instrument are actually a collection of astronomical objects that I've been talking about implicitly throughout, and those are pulsars. Again, it seems ridiculous to explain pulsars in this company, given the history, but of course they're rapidly rotating neutron stars that emit beamed radiation along their magnetic field axis, which might be offset from their rotational axis, so that when the pulsar spins around, it could swing that beam into our line of sight, which would register as a radio pulse in our radio telescopes. And we can use these as incredibly sensitive astronomical metronomes and time them incredibly regularly over many, many years and use the timing regularity to understand the dynamics of the pulsar, the dynamics of the binary system that the pulsar might be in, and really just use these as sensitive clocks to infer any possible induced deviations to the timing regularity caused by gravitational waves passing through the system. And of course, yes, there's a picture. I'm not sure exactly when that was from, but not long after the initial discovery of pulsars, there's a picture of Jocelyn. So how do pulsar timing arrays actually measure gravitational waves? How can they be sensitive to gravitational waves? Well, if we have a gravitational wave incredibly emphasized in this visualization, it would be wonderful if it showed up as a green grid passing through the Earth pulsar system. Again, I'd love a radio telescope as big as it appears there. It will cause length changes or distance changes in the separation between the Earth and the pulsar. And that will cause those regularly timed pulses to arrive a little bit earlier or a little bit later than expected. So we get these timing offsets, gravitational wave-induced timing offsets. Now, again, it would be absolutely wonderful if we could use one pulsar to do this. But unfortunately, pulsars are not perfect. They're stable rotators, but they're not perfect. There are intrinsic rotational instabilities in the pulsars that could manifest, at least spectrally, signatures that could look like gravitational waves. So we wouldn't just rely on one pulsar to do this, no matter how well timed it is. We would use an array of pulsars. So if we have multiple pulsars here, different color pulsars, all responding to a background of gravitational waves, all of those gravitational waves coming from all the different parts of the sky essentially add up incoherently and produce this random looking time series. So it's not the nice chirping waveform that you get in LIGO or other detectors. This essentially looks like a random time series, and that's exactly how we treat it, because this is modeled as a stochastic background of gravitational waves. So we can't just rely on nice template methods in the time domain to pick out the signal, but we can rely on the fact that these timing offsets created in these different pulsars are correlated between the pulsars in a very, very distinctive way that only depends on the angular separation of the pulsars on the sky. So we use this pulsar timing array concept as a way to pick out the influence of gravitational waves. And before I show you what that curve looks like and where it comes from, let me just visualize what the NANO Grav detector looks like. So this is as accurate as we can get it, the relative locations of the pulsars in the Milky Way, with Earth right here at the center. Even the spins of the pulsars here are as accurately represented in proportion to their true spin periods as possible. And so these are all of the roughly 70 millisecond pulsars that we use in our PTA gravitational wave detector in our little neighborhood of the Milky Way. So if we do imagine ourselves to be at the center of this network of pulsars, all of those pulsars are responding in some way in their timing to the gravitational waves passing through. And if we imagine that there were no gravitational waves present, then there would be nothing to correlate their timing properties. They're separated by hundreds to thousands of parsecs. But with gravitational waves being present, and with Earth as the origin point of the center of all of those observations of the radio pulses, the correlated jiggling of the Earth creates a distinctive timing correlation pattern between all of the pulsars. And so we get this quadrupolar-like correlation pattern in the timing properties of the pulsars that only depends on the angular separation of the pulsars on the sky. And then overlaid there were, again, those visualized cross-correlation data points from NANO Grav. All right, so one of the most common questions I get is, why that pattern? What is that curve? Where does it come from? So this is my best attempt to explain this without any contour integrals or any math at all. So if we imagine that this is a statistically isotropic gravitational wave background, and we plonk a little pulsar down in the sky there in green, the pulsar timing detector does not respond omnidirectionally sensitively to gravitational waves. And this is true for any gravitational wave detector. It will have some sensitivity to certain parts of the sky, some sensitivity to other parts of the sky, but it's not the same across all of the sky. So if we visualize how this pulsar would be sensitive to gravitational waves coming from different parts of the sky, it might look something like this. So the yellowish regions here are where the pulsar timing is responding positively to gravitational waves. The black regions are where it's negative, and then the purplish regions are where it's very insensitive to gravitational waves. And if you wanted to address that insensitive region, you might add another pulsar, which would kind of reduce some of the insensitive regions. And this might be the appropriate way to look at how you would fill out the sensitive regions on the sky if you were doing, say, a search for an individual source. But as I've been implying, when we search for a stochastic background, we're really looking at cross-correlated responses. We're doing a cross-correlation search for a background of gravitational waves. So really, we should be looking at the overlap of these response regions. And the overlapping region looks something like this. So the correlated responses looks like something positive here, negative here. Again, negative is fine. And then insensitive over here. So this pair of pulsars is actually relatively insensitive to gravitational waves coming from over here. Now, the way to distill that information into one number is just to integrate that correlated response times the isotropic gravitational wave background intensity over the entire sky, and that gives you a number. Okay, so it's just the gravitational wave background power, or the intensity, multiplied by the overlapping response functions, and then integrated across the sky. So when we do that, that gives you one number, and it turns out for this pair of pulsars, the positive regions roughly balance the negative regions, and you get almost zero response to gravitational waves. But if we do this with a different pair of pulsars, say one that's got pulsars much, much closer together, then the positive regions outweigh the negative regions, and you get a positive number. Same for this pair of pulsars. Positive outweighs the negative. And then you keep doing this with more and more pulsars until eventually you've mapped out this, what is known as the Hellings-Downs curve. So this Hellings-Downs curve, this very distinctive signature that lies at the heart of all of our gravitational wave detection statistics, is nothing more than how pairs of pulsars respond to an isotropic background of gravitational waves. And this curve also underpins our entire pulsar observation strategy and why we observe so many pulsars. Because our goal is to measure this curve, and therefore we need many, many pulsars spanning different angular separations to map out that curve at different scales. And so this is showing the growth of NANO Grav's array over time, starting in about 2005 with a relatively small number of pulsars, and then growing to encompass roughly 70 millisecond pulsars to the present day. So each of these strips is an individual pulsar. Each of the points corresponds to a particular observing epoch of the pulsar, and the different colors correspond to different radio observing frequencies. So you can just see the growth, and over time we've issued periodic data sets and upper limits on gravitational waves. They started to get very interesting towards the end, even the upper limits, because in our 11-year data set, we found we were actually sensitive to the particular version of the solar system ephemeris model that we were using. So we hit that sensitivity limit. We have to reference our observations back to the solar system barycenter as a sort of intermediate stage in our analysis. And JPL and INPOP and other groups update their ephemeris models periodically. We found out that we were beholden to our particular version of that model in our analysis. But with the inclusion of Juno data and some other refinements, we're no longer sensitive to that as a major source of uncertainty that we think. In the 12-year data set, we reported what we called a common spectrum process. This is a random process that was giving excess noise in our pulsars at low frequencies that appeared to be statistically uncommon across the pulsars, which was predicted to be the first kind of heads-up sign of the background, even before the very distinctive cross-correlations appeared. So it gave us hope that we were on the right track. And then in this 15-year data set, we have this compelling evidence for low-frequency gravitational waves linked to the cross-correlations between the pulsars. Now, since I was talking with Richard yesterday about how we calculate significance and background estimation, I thought I'd include this technical detail for those that are interested in the audience. A problem with statistical background estimation and actually getting sigma significances is that our signal is in all of the data. So how do you find a patch of your detector that doesn't contain the signal to try to estimate the background distribution? In ground-based gravitational wave detectors, you take the data streams from the different instruments and you offset them by the light travel time between the detectors. And you try to assess how often noise fluctuations alone could give you detection significances as large as you're seeing. But we can't do that in PTAs because the signal is permeating the entire data stream. The merger timescale of these black holes is potentially millions of years. And what we're seeing is the very early in-spiral portion of the waves of the system itself. So what we do is something similar in spirit. We do something called sky scrambles and phase shifts, which are attempts to augment the data in a way that still preserves what's in the data, the statistics of the data, but wrecks all of the possible cross-correlations between the pulsars. And that allows us to assess how often just noise fluctuations in the data could give us detection significances as large as what we're seeing. And so doing that and then combining with some simulations, which are just really a backup check, and then estimates of what the analytic background could be are roughly in agreement. And when we do all of those techniques, we're getting something in the regime between 3.5 to 4 sigma. That was just for the real statistical aficionados in the audience. All right, and then when you tot up all of the gravitational wave background detection significances, NANO Grav has that 3.5 to 4 sigma. The EPTA has around 2 to 3 sigma. PPTA around 2 sigma, and then the Chinese pulsar-timing array reports 4.6 sigma. They're using a different detection statistics though, and their data aren't public, so we can't actually validate the results yet. All right, so again, we need to visualize these correlations in some fashion. This is moving away from detection statistics and just visualizing what the correlation pattern would look like. So it's the equivalent of trying to make that chirping waveform visualization in LIGO. You might think that you take all of your pairwise correlation measurements, you just plop them into bins, and you make a plot, right? It's not as easy as that, and we only found that out about a year ago because the gravitational wave background is now strong enough that it's a major influence actually in the noise properties of the pulsars themselves. It could be the dominant noise influence at low frequencies in the pulsars. And what that does is it correlates those pairs. The fact that you've got the same pulsar in different pairs actually makes those pairwise correlation measurements themselves correlated. And so the bins in this plot are correlated, and it's just a caution to not try to rely on chi by eye when you're looking at this plot. The bins themselves are correlated, and the fit is very consistent with the Hellings-Downs curve. Now, when we look at the recorded spectrum of the gravitational wave background, these different violins here in gray are Bayesian representations of the measurement of effectively the power spectrum of the gravitational wave background at different frequencies, starting down here at a few nanohertz and then moving upwards to almost 1 over a year over here. In the blue, you've got the posterior envelope of power law fits to the gravitational wave background. And then in the black dashed line, you've got what happens if we if we keep the shape of that spectrum, that power law, fixed to a fiducial shape that we think it may have, and then just search for the amplitude. Now, when we look in the other pulsar-timing array collaborations, very nicely, they're all consistent. Okay, down here in the bottom, we've got all of the different overlapping Bayesian recorded power spectra. And then if we cast those power spectra to equivalent constraints on the amplitude and the spectral exponent of the power law, we get overlapping regions of the amplitude and spectral exponent. And there is some significance to what this spectral index is. I've said it's roughly 13/3 over here is our fiducial model. And if it gets close to that, we get rather excited because that's close to what we might expect, at least theoretically, from our target population, which are supermassive black hole binaries. Not just one, but a large population of supermassive black hole binaries, all adding together incoherently and producing this background of gravitational waves. Now, a good exercise that I did as a grad student, and that enthusiastic students in the audience can try, is to compute what the characteristic strain spectrum from a compact binary population looks like. You can do it on the back of an envelope. It's about f to the minus 2/3, and that just relies on some basic knowledge of gravitational waves and how they're emitted from binary systems. But unfortunately, in pulsar timing arrays, we're not directly sensitive to the strain. We're sensitive to timing offsets in the pulsars. And so when you convert that f to the minus 2/3 spectrum into the power spectral density of the timing offsets, that actually gives you something that's frequency to the minus 13/3. So we're looking at areas close to that. Obviously, we're not trying to just assert that. We want to measure it because any deviations from that spectral exponent of f to the minus 13/3 could indicate something very interesting about how the binaries are hardening and interacting in their final parsec of dynamical evolution. And for more detail on that, there are a variety of different processes that could be interacting with the black hole binaries at these very small separations. It should always be roughly frequency to the minus 2/3 at the higher frequencies, because there the black holes are very close together, and they're probably just undergoing evolution through gravitational wave emission. But at lower frequencies corresponding to larger separations between the black holes, you might have a variety of different dynamical interactions that is contributing to hardening the binary and getting it to smaller separations. And that could include things like interactions with stars in the central regions of the galaxy, potentially interactions with a circumbinary disk that could be extracting energy from the orbits as well, or even the presence of residual eccentricity of the binaries once they enter the PTA band. All of these things, by virtue of leaking energy into the wider environment rather than just gravitational waves, could lead the strain spectrum to tip over and create this nice feature, this turnover feature at lower frequencies. And ultimately, we'd like to measure where that is and measure the slope at lower frequencies to inform our knowledge of final parsec dynamical interactions of these massive black holes. In terms of what NANO Grav found, and broadly what the other PTAs found, supermassive black hole binaries can explain the population of, supermassive black hole binaries can explain the signal we've seen. And the way we approach that analysis is we adopt a population emulator approach. So we have this sort of tree of prescriptions to model galaxy mergers, and then populate those galaxy mergers with massive black holes, and then a phenomenological way of modeling how the binary hardens over cosmic time. Each vector of those parameters, those population parameters, generates a spectrum of realizations. And then we train, in this case, Gaussian processes as an interpolation method over that entire grid of different choices of initial conditions. Once we do that, that gives us a fast emulator of this lengthy process to generate populations. that we can connect onto our Bayesian inference pipeline and actually infer what each of these parameters actually is. We don't vary everything because there are so many here, but we vary some key ones. I'll talk about this package in just a second, but this is a rapid spectral analysis code that operates on intermediate products. Rather than starting from the original timing data, there's really no need if you're trying to infer astrophysics. So we've built a much faster method. I'll talk about that in a second. Also, we found, as many other fields have, that Gaussian processes scale very poorly with training data. So if we want to scale this to more complex simulations or more training data, then we're experimenting with normalizing flow neural emulators, which have been successful in some similar problems in other fields. So this rapid spectral estimation technique I'll just mention very briefly. This is the idea that we can operate on those Bayesian power spectrum distributions and refit against those instead of starting from the original timing data. If all we're interested in is fitting the spectrum and trying to infer what's creating that spectrum, shape parameters, et cetera, then we can operate on some intermediate analysis products and do in, the time taken less than the time taken to boil a kettle than days or weeks as traditional analysis methods might take. And Keffel means horse in Welsh. My graduate student who developed this named it. He wanted to call it Keffel because it kind of sounds like GFL, standing for the generalized factorized likelihood. All right, so what NANO Grav has found here, like I said, is that binaries can create this signal. What it does imply, though, is that the signal is slightly on the large side, which is meaning that the mass of black holes tends to be larger on the larger side and with very efficient orbital evolution with binary lifetimes less than a few gigayears. What you're seeing in this complicated plot is really the NANO Grav recorded data here, or our constraints on the amplitude and spectral exponent. And these different colored regions correspond to different ways of modeling certain astrophysical noise in our detector. So really just take this entire ellipsoid region here as what we've actually inferred. And then in the vertical dashed line here is that 13/3 expectation, this theoretical expectation. But of course, we're only seeing a realization of the population. And even gravitational wave only evolution can give you massive departures from power law behavior from realization to realization. And so you're getting variance in the population, which is shown in this purple region here. So that's even just with gravitational wave only driven evolution, you're getting massive realization to realization fluctuations, departures from that expected power law behavior. And that's exacerbated even further if you look at alternative methods of hardening the binary at larger separations, which can give this blue region here. So that's if you've got the binary in contact with the environment and undergoing stellar scattering or some other mechanism of hardening at larger separations. So we're slightly in favor of environmental interactions in a Bayes factor analysis, but it's marginal at best, and so we'll just have to keep tracking the analysis for longer. More data, more baseline, allows us to dig deeper into the spectrum and hopefully uncover evidence of that turnover and more cleanly measure the shape of the spectrum at lower frequencies. So as I mentioned, we're on the slightly larger side of predictions, but we're not in serious tension with predictions. This is the posterior of the amplitude of the gravitational wave background at periods of 10 years, and these are various modeled predictions throughout the years. So we are on the larger side. We're not in significant tension, but I still think there are interesting questions to be asked about how our results actually fit in with the broader picture of galaxy evolution and massive black hole dynamics within the centers of galaxies. What is clear, though, is that we're looking at the really, really extremely high mass tail of the supermassive black hole mass function. So in the dashed lines here, you're seeing the underlying massive black hole population, sort of the number density. And then at the various colored lines correspond to where they are in frequency, where those binaries are in frequency. And then in the solid lines, you're actually seeing what happens when you convolve that population with what PTAs are sensitive to. Gravitational wave detectors are sensitive, obviously, to the most massive black holes and ones that are relatively close as well. So the typical system that we're sensitive to and that we're picking up as a component of the background is something that's about 10 to the 9 to 10 to the 9.5 solar, something that's closer than redshift 1, and that favors mass ratios close to 1 as well, because that maximizes the strength of the gravitational wave signal. Now, this has been our study of the gravitational wave background so far, but it's really only the start of this field. Sort of my interpretation of what the future of this field looks like has this initial stage, and then we're making first steps in spectral characterization and trying to understand what's going on with this population that could be manifest in this signal. But then we'd like to find individual binaries that could be resolved out of that background. So over time, as we're staring at this background longer, individual systems should come into focus and rise above the level of other systems that are in particular frequency resolution bins. After that, my personal dream is that one of those individual binaries can be referenced to an electromagnetic counterpart, and then we get a multi-messenger supermassive black hole binary system. Whereupon we have a measurement of individual sources, we have constraints on the population from the stochastic background, which gives us a broader view of the binary population in the universe that then goes hand in hand with what the LISA detector is going to offer in the next decade. And then potentially, once we're able to move all of those binary systems out of the way, we might be able to unveil much weaker gravitational wave signals coming from the early universe, sort of early universe phenomena, inflationary signatures, etc. So in between spectral characterization of the background here and individual binaries, I've drawn a cloud on the road, not necessarily because I think there's something very uncertain, but because I don't think the first evidence for an individual pair of black holes is going to come from template-based searches. I think it's going to show up initially as anisotropy in this gravitational wave background at a particular frequency. And this is something that work that first started theoretically when I was here at the IOA. And the similarity here is that, in the same way that we've built maps for the cosmic microwave background, we would like to build maps for the nanohertz gravitational wave background, using some techniques that are actually directly adopted from the CMB community. So this is what it might look like if you had a binary population that was slowly being resolved out of just a confusion background. You see hotspots are starting to appear where you've got the location of individual signals, and some of these are brighter than the others, and you might lock on to these as just regions of excess gravitational wave power on the sky at particular frequencies that inform follow-up targeted searches for those gravitational waves using conventional template-based techniques. So we do search for anisotropy in the gravitational wave background already. We have greatest sensitivity to those directional fluctuations where we have the greatest density of pulsars. So this is some sort of arbitrary measure of the sensitivity to anisotropy in different parts of the sky, and where we have the greatest density of our pulsars here, we have the most sensitivity to where those fluctuations might be. I would have told you already if we'd found anisotropy in the background, so we haven't. We have no evidence of anisotropy yet, but our upper limits are best and most constraining near where we have those pulsars. If it is formed of a binary population, then it's possible that we could detect anisotropy within approximately 5 years or so. And we do have the prediction that as you go higher in frequency, the number of binaries occupying a particular frequency resolution bin steadily goes down. So you might expect more anisotropic fluctuations at higher frequencies as well. So that's all leverage against trying to discriminate the origin of the background as being astrophysical, formed of supermassive black hole binaries, or cosmological, coming from early universe signatures. Now, once we do establish that there's some anisotropy in the background, we might try to search for individual sources. We do this anyway, because why not? We can. So we have these template-based searches for gravitational waves. And if this is a rough cartoon of the pulsar-timing network with Earth right here in pulsars and then a binary up there, what happens is, as the gravitational wave washes through the network, the way we pick up the signal from the different pulsar observations is that we get these pulses propagating from the pulsar to the Earth through the perturbed space-time, like so. And the net result of that is we get a signature of the gravitational wave as it passes the Earth, and then another signature of the gravitational wave as it passed the pulsar in the first place. And those different echoes of the binary's behavior can be separated by thousands of years, basically the light travel time between the pulsar and the Earth. So you're getting imprints of what the binary potentially was doing thousands of years ago. This is true for all of the pulsars, so you get a common Earth term, a common component of the signal when the gravitational wave passes by the Earth, but then also another imprint from when the gravitational wave passed by this pulsar over here and this pulsar over here. So this is trying to stitch together lots of different imprints separated by thousands of years to understand what the source has been doing over that time. So in a way, it's allowing us to cheat and go beyond just looking at a decade or so of observations and pick up what the signal has been doing for many thousands of years, potentially. So even though we don't have a nice chirping waveform in PTAs, we do get interesting signal structure. This is what timing delay might look like in a particular pulsar. If you only had the component of when the gravitational wave passed by the Earth, you would get this monochromatic signal like this in blue. And that's just because over the observation time that we're looking at these pulsars, the systems, the binary systems of black holes are basically not evolving. But if you look at the total signal structure, you've got this lower frequency envelope corresponding to the imprint of the gravitational wave when it first passed by the pulsar. And that's obviously lower frequency because the binary has evolved upwards in frequency over the light travel time. And if you look at eccentric systems as well, you get lots of interesting structures corresponding to not only periapse passage at the Earth, but also the fact that the binary was much more eccentric in the past, and that all adds to the signal structure seen in pulsar timing. So as I said, we do search for these individual systems. We haven't found very convincing evidence yet of an individual source, but this map here is showing the distance, the luminosity distance out to which we can basically exclude the presence of a binary. And we can reach out and exclude binaries at larger distances where we have the greatest density of pulsars in the sky. That's where we have our greatest sensitivity overall. And it varies by maybe a factor of 4 when we go to the other part of the sky where we have fewer pulsars. In the red there, you've got individual pulsars, and then white squares are prominent galaxy clusters where we would be well informed to look for the presence of binaries potentially. White diamonds are prominent candidate binaries. One of the most famous is 3C66b, because that was thought to be a periodic source that could be a supermassive black hole binary. And then the black points are systems that have been observed as having periodic variations in their optical light curves. They're quasars that might be binaries through periodic behavior in their light curves. And so we search for those as well. As I see it, the path to finding a multi-messenger detection of supermassive black hole binaries in PTAs can be one of two ways. I think either we'll get gravitational wave localization on the sky, and then we can search within that localization region for plausible host galaxies and try to sift through until we can convince ourselves that we found the host, and then do dedicated follow-up. Or we look at all of these binary candidates that exist already, and I'm sure we'll get many, many more once the Vera Rubin Observatory comes online. We start tracking more sources. And then we do targeted PTA validation. We basically lock the sky location of our search onto the location of these candidates, and we try to test statistically for the presence of a binary, whether there are gravitational waves coming from this kind of system. So we're doing this exercise at the moment in my research group. We're trying to go through a dress rehearsal of what the localization and host galaxy identification might look like. This is what you might envision a near future pulsar timing array to look like. It's got about 100 pulsars, just over 100 pulsars. This is a signal to noise 15 detection of an individual system. The distance is about 160 megaparsecs, and the black hole mass is about 10 to the 9.5 solar. This is the gravitational wave localization region encased in white there. And then within that region, you've got galaxies that come from the 2-mass redshift survey. And so if we incorporate not just localization cuts on possible galaxies, but also distance cuts and mass cuts, that whittles the number of plausible host galaxies down to about 50 or so. And that might be still too large, so we need to assess other ranking criteria. But it's getting close to where we can consider doing targeted follow-up on the top-ranked ones of those. One new impact we found is that it's not just overall signal to noise that makes a difference of this for the localization region. It's proximity of the gravitational wave emitting source to the pulsars in the sky. The way the pulsar antenna response patterns for gravitational waves interact is such that they sort of squeeze the localization region, and you get big benefits for having a source close to where the pulsars in the sky. The catch-22, though, is that we're looking in the galactic plane mostly for those pulsars, and it's very difficult to see galaxies and other features through the galactic plane. So there's a catch-22 there. And our next process is going to be trying to compute tension between masses recorded in galaxy catalogs, what we've inferred in gravitational waves, and do targeted follow-up on these kinds of candidates. Really, we're trying to forecast what this first detection might look like. In addition, we might expect electromagnetic signatures from these kinds of supermassive black hole binaries if you've got circumbinary disk structures around such binaries. So the interaction of many disks around such black holes being fed by accretion streams from a broader circumbinary disk could potentially manifest accretion variability and then flux variability in the light curves seen in these kinds of systems. And these are the kinds of systems for which we have 300 or so candidates at the moment, and we'll have many more, as I said, when Rubin comes online. Again, we're trying to pursue this as an exercise to see how we can take such light curves and PTA data to fuse them together into a multi-messenger analysis and constrain the properties of these kinds of systems. So gravitational wave emission and something like Doppler boosting of radiation from those mini disks around the black holes actually map out the dynamics of the orbit in complementary ways. And it's possible that we could be sensitive to the same black hole binary system in both gravitational waves and EM. There's a region of phase space for which we are sensitive to both kinds of signatures. In fact, we've got a very experimental version of our multi-messenger analysis right now, working on some simulated data, where if we just map out the posterior on the total mass and mass ratio from gravitational wave observations, we get the blue region. If we do the same thing from optical light curves, we get the orange region, and the overlap region, where what we would actually get from a combined multi-messenger analysis, is collapsed quite nicely, and it's close to the true value. So I've been rambling on about supermassive black hole binaries because I think they're the most compelling target for gravitational waves in this band. But by and large, the high energy community and the cosmology community has really been engaging with our results and have been testing lots of different theories on these data sets. In fact, this is a visualization of the different citation connections back to the NANO Grav 15-year paper. If you've never used this paperscape, it's very fun. So this is astrophysics and maybe black holes over here. This is high energy phenomenology, high energy nuclear physics, high energy theory over here. So we've got a lot of engagement. Really the largest area of growth in this field has been from people interested in confronting their models with our data. And so as a very quick summary of what we're doing so far for cosmological interpretation, this is showing the full spectrum of gravitational wave frequencies. This is now converted to the fractional energy density of the universe in gravitational waves. These are sensitivity curves in the colored regions here of different gravitational wave detectors, both present and planned. And then these are sort of the gravitational wave spectral constraints converted into these units with median solutions for these different models shown as the colored lines. And on the top here are the tested inflationary models, including phase transitions, and then topological defects on the bottom, including stable cosmic strings, and then domain walls as well. So again, I would have told you already if there was evidence of new physics arising. We have no evidence for strongly constraining any of these models, except perhaps stable cosmic strings, which would produce a spectral shape that is more in tension with what we're actually seeing than cosmic superstrings, for example. We also search for fuzzy dark matter, ultralight dark matter, and although we're not seeing any evidence of that yet, we are getting comparable constraints to torsion balance and atomic clock constraints on the same source. So I did want to leave some open questions in PTA science because this is a really fresh and open field, and I encourage any graduate students in the audience that are interested to seek out potential ways that you can contribute to the field. Really, what's the origin of the gravitational wave background is the key one. How do we convince ourselves that it is supermassive black hole binaries? After that, could we potentially cross-validate with other avenues in astrometric constraints on gravitational waves? There are various people in the room, Jerry Gilmore and Chris Moore, that have thought about that potential avenue. After that, when will individual signals be found? How can we do multi-messenger astronomy with PTAs for these sources? And then what unique fundamental physics and cosmology could we do with pulsar-timing arrays that would help complement and be different from other fields? So these are all open questions in PTA science. I think the very near future for this field is exciting because we're about a year away from splicing together all of these data sets across the world and making one uber pulsar timing array data set that will be 115 pulsars long and maybe 25 years as a baseline. So this was a recent meeting of the International Pulsar Timing Array community about a week before we announced those results. Despite the smiles, there was a lot of tension because everyone was very focused on getting the results finished and everything settled and all of the ducks in a row. Additionally, in North America in the near future, with the loss of Arecibo, we're looking forward to the potential Deep Synoptic Array 2000, which is a 2,005-meter radio dishes forming a radio survey of the entire sky. And there's 30% of pulsar timing array NANO Grav time built into the concept itself. And then, of course, beyond Meerkat in the southern hemisphere, there'll be the square kilometer array, which we're enormously excited about and which have huge sensitivity and impact on pulsar timing arrays and radio astronomy in general in the near future. So although I'm here telling you this story, really this is the story written by many members of the NANO Grav collaboration and the International Pulsar Timing Array collaboration. And I did want to highlight the efforts of my particular research group at Vanderbilt that contributed to the core analyses throughout the story, including graduate students in the bottom left there, postdocs here, who've now gone on to some faculty positions, and then my faculty colleague at Vanderbilt, Jesse Runno, who I think is known to some people in the room as well, who works on spectroscopic searches for supermassive black hole binaries. So it's nice to have that electromagnetic angle as well. Thank you so much for listening to this story. I'm excited about what this future holds. And I will leave the open questions in PTA science to excite the imagination of the younger people in the room and potentially anyone else who's interested in this field. Thank you very much.